Yan Yi. Yeah. Okay, so
sorry, you're good to go.
Yeah, thank you. Okay, so welcome again, everybody, for the work papers session. And the first paper is on the possibility of basing cryptography on X not equal to BPP by Yan Yi Lu and Rafael Paz. The paper did get the Best Paper Award for Crypto to 2021. And Yan Yi, please give it up. Let me just say that for this talk and for all the other papers in this session, we're going to ask the authors to spend about 9 to 10 minutes, maybe hopefully 9 minutes for presentation. Then we have like ample 6 minutes for discussion. So please, prepare questions, and we have some time to discuss each paper. So you have an hour overall for the 4 papers. Anyway, so Yan Yi, please go ahead.
Yeah. Start to share. Okay, hi everyone. It's really my honor here to present my work on the possibility of basing cryptography on X is not equal to BPP. And this is a joint work with Professor Rafael Paz at Cornell Tech. So today we're going to talk about the notion of wave functions, which was proposed by Diffie-Hellma in 1976. One-wave function is unequivocally the most central notion in cryptography. On one hand, we know that one function is both necessary and sufficient for a branch of private key crypto primitives. And on the other hand, public key encryption of leaves transfer would imply the existence of one functions. Therefore, without one function, there's really no non-trivial computational crypto. However, proving the existence of one function is a very hard problem and would imply NP is not equal to P. Therefore, in the absence of a formal proof, people have just come up with this different one function candidates based on different computational assumptions. However, we know that if we can build quantum computers, then some of these assumptions are just broken, and we really need a formal proof. So in this work, we ask, can we prove the existence of one function based on weak assumptions about feasible computations? And perhaps the most believable and open conjecture would be X is not equal to BPP. Recall that X denotes the class of exponential time decidable languages, and BPP stands for the class of randomized polynomial time decidable languages. So our unproven minimal conjecture would be X is not equal to BPP. Informally, randomness does not exponentially speed up computation. To see that this is really a believable and a very weak conjecture, let's consider the factoring problem. So to factor a large number n, randomness seems not to be very much helpful, since even if we can toss a coin, we don't know how to factor a large number in polynomial time. However, if we have an exponential time algorithm, we can simply factor a large number n by a brute force search. So therefore, X and BPP are really two different things, and it would be crazy that the randomized polynomial time algorithm can emulate exponential time algorithm. So today, we ask, can we base the existence of one function on the very weak assumption X is not equal to BPP? So we show that there exists a standard nature problem called MKTP, and this problem, being hard on average with respect to two-sided error heuristics, is equivalent to the existence of one functions. And also, this problem, the same problem, being hard on average with respect to errorless heuristics, is equivalent to X is not equal to BPP. As we shall see later, MKTP is really a standard problem related to cohomology complexity and has been studied since the 70s. And the two notions of errorless Avg-case hardness and two-sided error Avg-case hardness are two standard notions used in complexity theory literature. So today we show that the only gap between the existence of one function and x is not equal to BPP is a seemingly minor technical distinction between the two standard notions of Avg-case hardness for a specific problem. So to present our main theorem more formally, let us look at some notions. First, let us introduce the notion of one function. So a function f is one way if it's easy to compute and hard to invert. And in this work, we also consider a notion of infinitely open one function where the inversion requirement is relaxed. And we only require that all attackers fail on infinitely many input length n, as opposite to for all input length n in standard one function experiments. Then let us introduce the notion of cohomology compacity. And the question here is, which of the following strings is more random? The first string is 1, 2, 3, 1, 2, 3, and so on. And the second string is like something looks really random. And the notion of cohomology compacity is used to measure amount of randomness in a fixed string. So for any string x, we let k of x denote the length of the shortest program that outputs the string x. More formally, we fix the universal Turing machine U, and we are looking for the length of the shortest program pi, which consists of m, w, such that the universal Turing machine U, when simulated on m, w, will output the string x. And the notion of cohomology compacity has a great number of applications. However, this is uncomputable. So we instead look at Levin's cohomology compacity. And in Levin's cohomology compacity, we are looking for the most efficient program that outputs the string x. And here, the efficiency is defined to be the sum of the length of the program and the logarithm of the running time. For example, if there is a program pi that outputs the string x within time 2 to the power of n over 10, and length of the machine is at most n over 10, then we conclude kt of the string x is at most n over 10 plus n over 10, that is n over 5. And the intuition behind this is that we charge for the size of the program and the runtime of the program simultaneously, but we only charge logarithmically for time to capture the intuition that polynomial time computations are relatively cheap. And here MKTP denotes the language of pairs of x, k, such that kt of x is at most k. We remark that MKTP no longer seems to be in MP, since we don't know how to verify this in polynomial time. And let us introduce the notions of Avg-case hardness that we rely on. We first introduce the notion of two-sided error Avg-case heuristic. So we say that a language L is in heuristic P if there exists an algorithm H, such as H of x will output the correct answer with very high probability over random instances. And then next, let us introduce the notion of errorless Avg-case hardness, which is also a standard notion used in complexity theory literature. We say that a language L is in average P if there exists an algorithm H, such that H of x will output the correct answer with a high probability over random instance. And if H of x doesn't output the correct answer, it is guaranteed that H of x outputs bot. So the difference between these two notions is that a two-sided error Avg-case heuristic is unaware of any mistakes. So if the heuristic outputs 0, it's unclear whether L of x is also 0. However, an errorless Avg-case heuristic knows it when making a mistake. So if H of x doesn't output bot, then it is guaranteed that H of x outputs the correct answer. And in this work, we actually consider the BPP analog of these two classes, and the difference of these two classes remains the same. So we are ready to present our main theorem formally. We show that the existence of infinitely open one functions is equivalent to MKTP is not inside heuristic BPP. And x is not equal to BPP is equivalent to MKTP is not inside average BPP. So basing one functions on x is not equal to BPP boils down to a seemingly minor technical problem. And we show that proving the implication that MKTP is not in Avg-BPP implies MKTP is not in heuristic BPP is exactly what we need to base infinitely open wave function on x is not equal to BPP. And we remark here that we can also characterize standard one-way functions by considering an almost everywhere notion of Avg-case hardness. So it seems that this implication is really important to us, and we really want to prove this. But the next theorem says that, okay, if we want to prove this implication, we have to prove NP is not equal to P. So there are two ways to interpret this theorem. And the pessimistic interpretation would be that closing this minor gap will be very hard. And the optimistic interpretation would be that this is a new algorithmic approach towards proving NP is not equal to P. Just solve the MKTP problem errorlessly on average, having access to a two-sided error heuristic for the same problem. And let us mention some related work. First, Allen et al. Shows the X completeness of MKTP with respect to P/poly reductions. They show that if X is not inside P/poly, then MKTP is not inside P/poly. And Liu aspect 20 shows when functions exist if and only if this time-bounded cohomology complexity is hard on average. So this time-bounded cohomology complexity problem is another cohomology complexity style problem. However, it is unknown that this problem is X-complete. However, the problem we look at today is X-complete. And concurrently and independently, Ren and Sarnan also shows an equivalence between one functions and mild Avg-case hardness of MKTP. So in conclusion, today we have seen that the only gap of basing infinitely open one functions on X is not equal to BPP is the seemingly minor technical problem. However, proving this implication also shows that NP is not equal to P, which gives us a new algorithmic approach towards solving the NP versus P problem. And thank you for listening, and questions are welcome.
Thank you. Questions? Please feel free to unmute yourself and ask, or ask on the chat.
So, question here.
Yeah. Yes, Chris.
Can you say more about what it means to prove that this implication also proves P not equal to NP? That somehow parses a bit strangely to me. Can you expand on that?
Yeah. So basically, this theorem says, okay, if this implication holds, then the consequence of this is that NP is not equal to P. And so basically, the way we prove this is basically through our main theorem. So so if this implication holds, then there are two cases. One case is MKTP is not in Avg-BPP. Then we have one function, therefore NP is not equal to P. And second, if MKTP is in Avg-BPP, then we can reach a contradiction. So basically, we are saying that if this implication is true, then NP is not equal to P. So like anyone proves this implication would also prove NP is not equal to P.
Yeah, I think I see now. Thanks. Yeah, thank you.
Yeah, thank you for your question.
Okay, so any other questions? There are a bunch of questions on the chat. Does somebody want to unmute and ask, or should I read?
Yeah, my question was same as Chris's question, so I think it was answered. Yeah, thanks.
Okay. So let me pick one of them. So the question is there something interesting to say about the hardness against algorithms that make one-sided error?
I think make one-sided error. It depends on which one side like you are. So if you making no mistakes on yes instance, but only errors on no, I think like that case is like similar with this errorless case. However, if you can make mistakes on yes instances, but you make no mistake on no instances, the case is more similar with this two-sided error Avg-case hardness. So it really depends on which side the mistake happens. Yeah, is that clear?
So there's another, yeah, thank you. So it's another question here. So what if we assume P is not equal to NP, then can we still hope to prove the implication?
Yes, of course. If we assume P is not equal to NP, then there's no contradiction.
Right. Okay.
So this implication is like only it's like only weaker.
Right.
Yeah, thank you for your question.
Yeah. So another question, kind of like maybe open-ended. So you're talking about building one-way functions from Kolmogorov complexity, the hardest of Kolmogorov complexity. What about building other primitives directly from hardest Kolmogorov complexity, not just one-way functions? Do we have chances to do something nice there to break some, black box impossibility results, etc., or not break, but go around?
Yeah, this is a great question, and I think we are still working on that. And right now, it seems there's not much hope, and we don't even know like how to base regular one-way function on Kolmogorov complexity. So yeah, but we are keep working on this.
Okay, thanks.
Yeah, thanks for the.
Thank you. So thank you again, Nini. It's a great result. Congratulations again. And okay, so let's move on to the second paper in the session. Just a second. So the second paper is in linear cryptanalysis of FF3-1 and FEA. And this is, as we said earlier, is the best young researcher paper award winner, and also honorable mention for the best paper award. And the author is Tim Bain. And Tim, please go ahead.
Thanks. So in this work, I'll present new attacks based on linear cryptanalysis of format-preserving encryption standards. So format-preserving encryption allows you to encrypt a plain text that has a certain format, like, for instance, a 6-digit integer, so that the ciphertext has the same format. So for example, if you're encrypting the 6 middle digits of a credit card number and you have a legacy system that only allows you to store 6-digit integers, you need this. Of course, because there aren't many 6-digit integers, this would give codebook attacks. So that's why we need a tweak, which is like an additional public parameter. And so if you change a tweak, ideally you should get a different looking block cipher. So there are standards for this in the US. There's the NIST standards FF1 and FF3. In South Korea, there's the FEA family of block ciphers. And the attacks I'll present apply to FF3-1 and then this FEA family, but not to FF1. So these ciphers are Feistel ciphers. And in the case of FEA-1, it's a really classical Feistel cipher. You're basically XORing the branches. And in the case of FF3, the branches are added using a modular addition. Now, there's a bunch of other differences that we can mostly ignore, but what they have in common, and this is really important, is that the tweak is split into two parts. There's a left tweak and a right tweak, so TL and TR, and these are used in an alternating way. So, for example, in the even rounds, we always use the right tweak, and in the odd rounds, we always use the left tweak. And that will be the basis for the attacks. So there have been, of course, there has been a lot of work on the security of FISO ciphers, generic security. So even at the time of the design of FF3, it was known that you can distinguish such a construction with some amount of data. And later on, it was also shown that you can do message recovery. So then at Crypto 2017, there were a number of dedicated attacks on this NIST standard, FF3, where it was shown that there's a flaw in this tweak schedule, and that leads to slide attacks. Of course, NIST did respond to those attacks, so they modified the tweak schedule. That's why I'm talking about FF3-1. And this modification destroys this, this dedicated attack. They also required that the domain size is at least 1 million. And that doesn't completely prevent the generic attacks, but it does make them essentially much harder because the amount of data you need grows with this n. So the new attacks will be essentially generic, but we use this property that the tweaks alternate. That will be really important. And the data complexity of the attacks is about the square root of the data complexity of previous attacks. So that shows, for example, that this NIST requirement of minimum domain size of 1 million really isn't enough. So I'll try to give a high-level idea of how this attack works. So suppose you take a random 4-bit function. So you just, from the set of all possible 4-bit functions, select one uniformly at random. And then you look at this output distribution of this function. So you count how many inputs are mapped to a given output. And then actually, typically, this distribution will not be very uniform. If it was a large random function, it would be pretty close to uniform. But for small functions, there's actually a lot of variability. So there's a good chance that you don't get a uniform distribution. And another way of thinking about it, which I'm not going to go into too much here, is that you can take the Fourier transform of that distribution. And that means we're going to look at which linear combinations of outputs of this function are highly biased. That will be very closely related, of course, to linear cryptanalysis. So what can we do with this observation about non-uniform output distributions? Well, so remember, we have this alternating tweak property. So what happens if we fix, for example, the left tweak? So now actually this F1, so before it was actually a big function, had many inputs, but now it has not too many inputs because the domain is typically small. So that means that the output distribution of F1, so that's the distribution when the right half of the ciphertext, left half of ciphertext, of plaintext, sorry, and the right half of the tweak are all uniform random. So that distribution will be not uniform in some way. And actually this output is just the same as the sum or XOR of the left half of the plaintext and the left half of the ciphertext. So that would be a 2-round distinguisher. Of course, we need to somehow quantify what it means for this to be non-uniform, and we also need to iterate this over many more rounds. And that's what we're using linear cryptanalysis for. So if you do the analysis, you find that there's an iterative linear trail. So that's the one actually shown here on the right, which has a pretty good correlation of 1 over this domain, square root of domain size to the power of over 2. So for FF3, it's a little bit different because we have these modular additions, but it's not a real problem because we can just use a generalization of linear cryptanalysis to the group of integers mod n with addition. And if you do a little bit of additional tricks, you can get the data complexity of this distinguisher down to something n to the power of over 2 minus 1. But this isn't optimal yet because we're just using one approximation. There's only one mask U, one linear combination of the outputs that we're using, but we could use any. So this is a good step in the analysis, but we really need to use all of them. And since actually the set of all these values U that we can use is a vector space, we can use what's called multidimensional linear distinguishers. So an easy way to sort of describe that is by what's called a chi-squared distinguisher. So what we do here is we estimate an output distribution. So in this case, it will be the distribution of the left half of the plaintext plus the left half of the ciphertext. We make an empirical estimate of that, and then we basically compute the Euclidean distance from that estimate to the uniform distribution. And because of the linear analysis we did, we know more or less what this chi-squared statistic should be, and we also know it's going to be quite large. And so this is then a distinguisher, and it's a distinguisher with a data complexity which is about a square root of n better than just using a simple linear distinguisher. So of course, in practice, it's always very interesting not to just have distinguishers, but also message recovery. And what this means is that, and this is the same as for previous message recovery attacks, given the ciphertext of a secret message encrypted under many different tweaks, we want to recover that secret message. So how it will work is, for example, we estimate the distribution of the left ciphertext for a known message, PLPR, and then we do the same thing for an unknown message, which is just the same, except that, for instance, the left part, there's an unknown difference added. And then actually these distributions, they will be related to each other. In fact, they will be just shifted roughly by this difference delta. So in this case, actually it's shifted by 1, right? Because 0 and 1 are kind of flipped in this histogram. And so that attack essentially requires about the same amount of data as the distinguisher. And for right half recovery, you need a little bit more data. So to conclude, so I've tried to explain the basics, at least, of two attacks, 3 if you count the linear distinguisher, on FF3-1 and FEA-1, which require about square root of data as previous attacks. And in the paper, I also describe some attacks on FEA-2, which require the cube root of the amount of data of previous attacks. But then again, FEA-2 has more rounds. And also how to turn the message recovery attack for FEA-1 into a key recovery. So what's the impact of this? So of course, so the attacks, I should say, can be completely practical, but some applications don't allow you to use a lot of data. Sometimes the domain size is large, so smaller domain size means you're more vulnerable. The big problem here is essentially that every application of these standards needs to be carefully checked. So that's something you definitely don't want normally from a block cipher. For example, if you want for the NIST standard FF3-1 the same security as before, you would have to use a minimum N of 1 million as opposed to 1,000. But that's just, I mean, you cannot do that because that would ruin a lot of applications. So the real thing to do here is, of course, to fix the tweak schedule. So for now, I would say just avoid these standards. I don't use them if you're not already using them. If you're already using them, definitely check that you don't rely just on indistinguishability, because that's typically even easier, not in terms of data, but in terms of the practical conditions. And definitely don't use small domains. So that's everything. So this link here, you can follow that for the source code of the attacks, and if you want to compute exactly how much data you would need for the parameters that you're using. Thanks.
Thank you, Tim. Thank you very much. Any questions? Please feel free to unmute yourself. So there's a question in the chat. Why did this standard use left-right tweaks?
Good question. Why? I don't know why because for instance, FF1 doesn't, and that doesn't have the problem. So I guess that in the case of FEA, it's more or less because FF3 used it, because it's a later design. I guess it makes it. I mean, one way could be like if you want a longer tweak. I mean, you can only put so many bits of tweak every round, so then you can have a twice as long tweak. Maybe that's a reason. Although there are also different ways of achieving that.
In fact, were there any security claims, or either formal or informal, coming with the design, or did it just design come from above?
So yeah, I mean, of course, the security of generic Feisel ciphers is quite well understood, but the problem is it's not so well understood for, well, I guess that if the domain size is small, that's hard to get a good results, let's say. So that the main focus on Feisel ciphers has been when the domain size is large. But yeah, there has been a lot of previous analysis on this scheme. So yeah, but well, still it was broken. Yeah.
So another question in the chat. Were you able to identify this flaw by modeling the primitive in something like EasyCrypt, or you found it by inspecting the spec?
I just found it by looking at it. Yeah. So yeah, I just went through linear cryptanalysis directly. Yeah.
Mm-hmm. Okay. So Or has a comment that due to this attack and the improved versions of 10, but this is which has similar complexity, ISO decided not to standardize FPE at the moment. So at least this.
Yeah.
Yeah. Okay, any more? So if there's no more questions, then Tim, thanks again. Congratulations for the result.
Thanks.
Thank you. Nice. And let's move on to the next paper in this session, which is efficient key recovery for all HFE signature variants by Chengdong Tao, Albrecht Petzold, and Jin Ding. And this is an honorable mention for the best paper award. Please, who is going to give the talk? Albrecht is going to give the talk, so please go ahead, Albrecht.
Thanks. Can you see my slides?
Yes, thank you. Yeah.
Okay, so thank you for the introduction and welcome to my talk on the efficient key recovery for all HFE signature variants. So my name is Albrecht Petzold, and this is a joint work together with Chengdong Tao and Jin Ding. So first, where are we in this talk? So we are talking about post-quantum cryptography, and in particular multivariate cryptography. And here we are in the field of big field signature schemes. This means that we have a central map, F, which is a univariate map over an extension field, FQ to the N. And we have an isomorphism phi between the vector space FQ to the N and the extension field. And due to the special structure of the map F, the map F bar phi to the -1 circ F circ phi is a quadratic map over the vector space FQ to the N. An important example of such a big field signature scheme is the HFEV- signature scheme, which combines the idea of big field together with the minus modification and the miniature variation. The central map of the scheme is a map from FQ to the V times the extension field to the extension field, and it has this form shown in the slide. So the important things here are that the degree of the polynomial is bounded by big D, and we have here these linear maps beta I and the map quadratic map gamma in the so-called miniature variables. Then we choose randomly two linear maps T and S of maximal rank, and the public key is given as P is T circ F bar circ S, which is a quadratic map from the vector space FQ to the N plus V to the vector space FQ to the N minus A. And the private key consists of the three maps S, F, and T, and therefore allows to invert the public key. There exist basically two attack strategies against the HFEV- signature scheme. The first one is a direct attack, which is a signature forgery attack. And here we find that the degree of regularity is bounded from above by this formula here, which depends on the degree bound, the number of minus equations A and the number of villager variables. The second attack strategy is a min-rank attack, which is a key recovery attack. And when solving the min-rank problem using the minors approach, the complexity of this attack can be estimated by this formula here. In our paper here, we propose a new min-rank attack against the HFE signature variance, and the complexity of our attack is given by this formula here. So the main differences are that our attack is completely independent of the number of minus equations, and V only appears in the first row, which means that the complexity of the attack is polynomial in the number of villager variables. So to describe our attack, we need a number of preliminaries. So first we use the so-called matrix representation of the HFE central map. Namely, we write the HFE central map as a quadratic form with a matrix F star 0. And we can easily compute the Frobenius isomorphism Fq to the k from this formula. And here we get the matrix F star k. Furthermore, we use a matrix representation of our isomorphism between the vector space and the extension field. And to cover the villager variables, we define a matrix M tilde, which is a block matrix containing M and the identity matrix for the villager variables. And by doing so, we get the following relation between elements of the vector space and elements of the extension field. So now let S and T be matrices representing the linear parts of S and T. And from our quadratic form of the central map, we find the following. And if we denote here M tilde to the -1 times S tilde to the S to the -1 by U, and M to the -1 times T by W, we get the following, which I call the fundamental equation, and which will play a major role in our attack. So here we have again our fundamental equation, and the main step of our attack is to recover the first affine map S. And we observe here that if we denote by U the first row of the matrix U, and by BI the first row of U multiplied by the matrix representing the public key, then we define a matrix Z as a matrix whose row vectors are given by the BI, and then the rank of the matrix Z is at most D. And the second important observation is that the first n rows of the matrix U are completely determined by its first row. So how does our attack work in a nutshell? So since we have U is M tilde to the -1 times S to the -1, we can find S by finding U. And due to our lemma, we only have to first find the first row of U. And if we denote the first row of the matrix U by the vector U, we find that we only have to, or that we can assume that U0 is equal to 1. And since the rank of the matrix Z is smaller or equal to D, we can find the unknown element U1 to UN plus V minus 1 by solving a min-rank problem over the base field. The remaining rows of the matrix U can be chosen at random such that U is invertible, which means that we have found S. And having found this matrix S, it is easy to recover F and T. It is basically only solving some systems of equations. For the complexity, the most costly step of our attack is the solution of the min-rank problem, that we need to recover U and S. And when doing this using the minus modeling, the complexity of this step is given by this formula here. So this table shows the application of our attack on the GEMS signature scheme, which is one of the third round candidates in the NIST standardization process. And we see that especially for the high security levels, the proposed parameters for the scheme don't reach the required security levels. We find that speeding up the signature generation process of the scheme by decreasing the degree bound while increasing A and B is not possible, which make the modifications as in blue games and red games impossible. And third, we note that for high levels of security, we need very high values of the degree bound D. For example, for the highest security level, we need small d is greater or equal to 20, or big D is greater than 500,000, which will mean a drastic slowdown of the signature generation process of HFE- and GEMS. Therefore, we come to the conclusion that the techniques used in GEMS don't suffice to create an HFE-based signature scheme, which is both efficient and reaches high levels of security. And to conclude, so in this paper, we proposed a new min-rank attack against HFE signature variants. The complexity of our attack is exponential in the degree bound D, but it is polynomial in the number of signature variables, and it is independent of the number of minus equations. Some consequences. So first, we can't speed up the scheme by decreasing D while increasing A and B. And we find that for high levels of security, we need a very large value of the degree bound D. And this arises the question if we can build an HFE-based signature scheme, which is both efficient and offers a high level of security. So thank you for your attention, and for more information on our attack, please watch the 20-minute video talk or read our paper. Thanks.
Thank you very much, Albert. Any questions? Please feel free to unmute yourselves. More. Okay. Okay, so if there are, oh, here's a question by Daniel Leipen. He read it on the chat. Min rank attacks have hit multivariate signatures really hard in the past. Do you have any idea how close we are to a theory that the min rank attacks are exhausted as an approach?
I think that the authors of the new min-rank papers recently tried to use every information that they are possible to get, and therefore I don't think that there are main possibilities to improve the min-rank attack anymore. But it's only my opinion.
Okay, thank you. More questions? Okay, so I think there's some probably discussion here anyway. So thank you again very much, Albrecht, again for the great result. And let's move on to the last paper of the session, last but definitely not least. 3 halves makes a whole, beating the half-gates lower bound for garbled circuits. Again, honorable mention for best paper award. Mike Rosulek, Lawrence Roy, and Lawrence, I assume, will give the talk. Please go ahead.
Thanks. Hi, I'm Lawrence Roy. I'd like to show you our new garbling technique, sliced and diced garbling, where 3 halves come together to make a whole. Garbled circuits are one main technique used for secure function valuation. One party becomes the garbler and the other the evaluator. The garbler sends a kind of an encrypted circuit to the evaluator, who runs it. This keeps the values in the circuit secret from both of them. Sending the garbled circuit is a bottleneck of the protocol. Ever since Yao invented garbled circuits, researchers have been improving them. This plot shows the cost of garbling a circuit consisting of an AND gate and an XOR gate. ZRE15 found that XORing together two half gates makes a whole AND gate with only 2 ciphertexts worth of communication. This was the state of the art for 6 years, and it was even proven optimal in a restricted model. However, in our new garbling scheme, an AND gate can now be garbled with just 3 halves ciphertexts, while maintaining compatibility with free XOR. In a garbled circuit, the function f is broken down into gates connected with wires. Here's a wire carrying 1 bit. The garbler will encrypt the circuit. Each wire is given 2 random, unguessable strings called wire labels, representing false and true. The validator will only ever know one of the 2 wire labels for each wire, and must not learn the other label. To hide which wire label represents true, the garbler samples the point and permute bit pi a. The labels A0 and A1 are swapped if pi a is 1. Free XOR requires that A0 XOR A1 always be delta, the same for all wires. This key optimization allows XOR gates to be validated by simply XORing the wire labels together. The validator will need to know whether it has A0 or A1, so the first bit, called the color bit, of AI is set to I. In a classic garbled circuit, the non-XOR gates in the circuit become encrypted lookup tables, where given only a single wire label from each input wire, only a single output wire may be decrypted. The garbler gives the evaluator an encrypted gate consisting of the 4-gate ciphertext G00 and so on. Let's see the output wire label representing false. An AND gate has 3 ways to evaluate to false, C, and 1 way to evaluate to true, C XOR delta. When the validator gets inputs AI and BJ, it can only decrypt Cij, the correct output wire label. Our new garbling scheme depends on taking a linear algebraic perspective on garbled gates. I'll start out by deriving it for these classic garbled AND gates. The garbled gate consists of 4 ciphertexts. A secure way of encrypting them is to hash the input wire labels and XOR that with the output wire label. Each output wire label of Cij is either C or C XOR delta, based on the truth table. Rearrange the equation so that the variables that the validator solves for are on the left. These linear equations specifying the garbled gate can now be written with linear algebra instead, by stacking them together. The 1-0 case is the true case, and so it involves delta. To represent this, we add a vector that is multiplied by delta. And then this gives us the full gate equation. The garbler can use this to find the gate ciphertext Gij and the false output wire label C. Then we notice this equation is underdetermined. That is, G00 is redundant and can be set to 0, as long as we solve for the false output wire label C. This optimization is called row reduction. The next optimization, half gates, works by combining hashes together in a way that creates redundancies. It uses h of a XOR b instead of h of ab. This is the gate equation for half gates. For the equation to be solvable, we need the right-hand side to be in the column space of V. The hash matrix has rank 3, as every column has an even number of 1s. So the gate matrix V only needs 3 columns to make this happen. The garbler must then solve for 3 things: 1 output wire label and 2 gate ciphertexts. However, the truth table does not have an even number of 1s, so it is not in the column space. To make this equation solvable, a control matrix R is added, which tells the evaluator to XOR the A input into the result when B's color bit is 1. In the second and fourth rows, A0 is XORed in, and in the fourth row, delta is XORed in as well, because in that case, the evaluator has A1, not A0. Solving for 4 equations and 3 unknowns is possible because the equations are linearly dependent, which comes from using hashes like h of A0 that can be found in 2 cases. More compression requires creating more redundancy in the hash calls. In this diagram, the 4 points are the 4 evaluation cases, AI, BJ. Each hash is a line through the points it can be evaluated at. For example, the lower left point is the A1, B0 case, where the evaluator can compute h of A1 and h of B0. Taking the XOR of the 2 inputs gives another pair of true and false wire labels. This is unused potential for hash calls. What happens if we hash them? We get 2 new hash calls, which can each be computed in 2 out of the 4 cases. E.g. in the A1 B0 case, we can compute h of A1 XOR B0. Although we'd like to get more compression from these extra hashes, saving a whole ciphertext seems to be impossible. Let's save half a ciphertext instead. Split the wire labels up into two pieces. This doubles the linear algebraic dimension, making room to fully use the 6 hash calls. In each of the 4 cases for the inputs A and B, there are 3 hashes that the evaluator can compute. The hash produces only a half of a wire label of randomness. It still has full-sized input though, as otherwise it'd be insecure. The 3 half-sized hashes combine together to make a whole wire label worth of randomness, which is used to mask the whole output wire label. The hash term in the gate equation will then look like this. Notice that after slicing, we now have 8 rows instead of 4, because each case evaluation must now produce a 2-dimensional vector as the output wire label. Every row of m XORs to 0, so m has rank 5. For this equation to be solvable, V must be a basis for m's 5-dimensional column space. The garbler must then solve for 5 half-sized variables. 2 of these are the 2 false output wire labels because of row reduction, or the 2 halves of it, I mean. The other 3 must be the gate ciphertext. Since they are half-sized, if we can get this to work, then we have a 3/2 ciphertext Garbling AND gate, as promised. Is our gate still secure? Assuming that the evaluator gets the input wire labels, assume that the evaluator gets the input wire labels A0, B0. The things that it can compute are highlighted in red. Any other evaluation case depends on 3 hashes, only one of which is known to the evaluator. The 2 unknown hashes are enough to completely hide the gate output. Here's the complete gate equation. The control matrix R must consist of 2x2 blocks in this form, based on the wire labels the evaluator knows in each case. Again, we need the right-hand side of the equation to always be in the column space of V. Like with half gates, the truth table causes the most trouble because we need to pick the control matrix so that R XOR T fits in the column space. However, this is a bigger issue than it was for half gates. Slicing requires creating an asymmetry in the column space of V, which forces the control matrix R to depend on which case outputs true. From R, the evaluator could compute the point and permute bits and learn the plaintext values. Our solution to this problem is called dicing. The idea is that the evaluator doesn't need to know the whole control matrix. It only needs to know Rij, which tells it what to do in the one case it is evaluating. The garbler rolls dice to randomize the choice of R so that Rij leaks nothing. It then garbles the control matrix by encrypting each Rij with the input wire labels, so that the evaluator cannot learn more than Rij. For this to work, we need a distribution on control matrices that always puts R XOR T in the column space and does not leak the truth table T to the evaluator. The way to do this is to first find a solution RT, which always exists, then hide it by picking a random valid control matrix R$ that's in the column space. Picking R$ from as wide a space as possible masks it, or makes it completely hide RT, completely masking the truth table. I'll now summarize the evaluation process. First, the evaluator uses H', a hash function outputting 8 bits, to decrypt the garbled control matrix. Zij is the corresponding control matrix ciphertext. It then uses half-sized hashes in the control matrix to evaluate the gate and get the output wire label Cij. Our garbling scheme bypasses the half gate's lower bound by using 2 ideas not present in their model. They assume a monolithic wire label, while we slice them into halves and operate on them independently. Dicing hides some of the coefficients of our evaluation equation, while they assume that the coefficients are all fixed in advance. We have several more results which didn't fit into this talk, including hiding the truth table of arbitrary gates, compressing the control matrices down to just 3 bits. Please check out the paper or the video for more. Thank you.
Thank you very much. What a great talk. Any questions? So Nigel is asking, can you get further savings if you slice the wire labels into more than 2 components?
I was hoping somebody would ask that. Sorry. So it's a subject of ongoing research, but here's sort of a sneak preview of like why that might not be the case, or why we might not be able to do better. So if we split into S parts, And then there's m they make the hash function output an m-dimensional vector. Then get a hash matrix that's 4s by 6m. You want to lower bound the rank of m in order to lower bound the number of ciphertexts. So then if we look at just one case of evaluation, the thing is it must fully hide the output from the evaluator, even if the evaluator knows another case. So just from 2 hashes, it must be fully random. So that means that of the 3 non-zero columns, like the values that's the 3m hashes it can evaluate, after deleting m of them, there must be, it only uses 2m hash remaining columns. So that's like an upper bound on the rank. So S must be less than 2m. And then second, there's like a kernel of this matrix M. And so the rank of M is the columns minus the size of the kernel. And anything in the kernel also constrains this matrix here, puts another bound on S, upper bound on S. Then if you combine these 2 upper bounds together, we get that the number of ciphertexts has to be at least 3 halves. So according to this rough analysis, it seems that we can't do better using our technique.
Thank you. Can you say a word on the assumption of the hash function that you flashed, I think, in the last slide?
Sure. Last slide. Yes. So there's like there's like a correlation, circular correlation robust hash function assumption, which is like says that if you have some secret delta, then and the hash function h of delta XOR x is like a PRF as a function of x.
That's not an assumption, right? That's not an assumption that for this paper, right? That's something that was just before.
Yeah. So then there's a stronger assumption that's called the tweakable CCR, which normally Garbling needs because you need to tweak the hash function for every gate.
Okay.
And it introduces a tweak. The thing is, it's more expensive to realize. It requires 2 AES calls rather than 1. Whereas we realized that we can instead make a weaker version of the tweakable circular secure robust hash function that's isn't quite as strong, but is still good enough for Garbling, and it can be instantiated from CCR and a universal hash. So that's like 1 call to AES rather than 2.
Got it. Thank you. Any more questions?
Oh, and just to add to that, there's a sort of a trick that lets Garbling get away with 1 normally, but it didn't work for this, and that's why we needed to use this new technique for the hash.
Great. So while people are thinking of typing up questions, just a small nit, for old fogies. So I think for your first slides, I think the first kind of whiff that you got from Garbling was like thinking the YAO 85, not 82. And even then was implicit, but never mind.
Oh, sorry.
Yeah, I think people also, I know it's previous millennium, who knows, who cares, but yeah. Anyone has something more meaningful to say, a comment, ask? Yeah, okay. I might just be right. Okay. Okay. So again, thank you very much. The speakers, thank you very much. And thank you, Lawrence. Thank you all the speakers of the session. So again, thank you. And I think we are